Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. We have been looking at various subsystems of a computer. Specifically, we started looking at the memory subsystem. In the previous lectures, we have been looking at cache design. We looked at different types of caches. We looked at direct mapped cache, set associative cache, fully associative cache, how these different types of mappings work, and we also looked at the performance of these different types of mappings. So, what we will look at in today's lecture will be another part of the memory hierarchy, which is the virtual memory. So, what we will look at is some fundamental concept that we have behind how virtual memory works, and then we will look at the details of how virtual memory is actually implemented. So, let us take a look at our memory hierarchy just to refresh what we already know. So, we have the processor with its registers and a primary cache, typically an L1 cache, which is located together, and then the secondary cache, which will be off chip. So, the registers and the L1 cache will be on chip, and then you have the main memory and the secondary memory. So, what we have already looked at is this part of it, that is how data goes from main memory to cache. So, that is what we looked at in terms of the caching subsystem. What we need to look at today is this part of it, that is how data is transferred from the secondary memory to the main memory. And remember that with respect to size, as we go from registers to secondary memory, there is an increase in size, but as we go from secondary memory to registers, you have an increase in speed, and there is also an increase in cost per bit. So, the combination of all these different types of devices is to optimize on the cost, at the same time obtain higher speeds and larger sizes. That is our overall goal. I would like to have increased size and increased speed, but at lower costs. That is what we are trying to achieve. Okay. So, we saw how that is done using with the help of caches, how we are able to speed up the execution by transferring data from main memory to cache. Now, we will look at how data can be transferred from the secondary memory to main memory and what is the purpose of doing that. So, this part of it is what we call as the virtual memory system. So, let us look at the why, what and how of virtual memory system one by one. So, why do we first of all need this thing called a virtual memory? As I said, in the design of any computer system, we need to provide a large and fast memory system at an affordable cost. So, that is what we need, right? It should be large, it should be fast, and the cost should be affordable. So, we are looking at architectural solutions which will help us to increase the effective speed and the size of the memory system. So, that is what we are trying to do with having a hierarchy of devices in the memory system. And if you look at cache memories, the cache memories help us to increase the effective speed of the memory system, whereas virtual memory is an architectural solution which helps us to increase the effective size of the memory system. So, remember we said that we wanted to have a large and a fast memory at an affordable cost. So, what we are trying to do is fast memory we were able to get the help of cache by using fast devices. Large memory, that is what we are trying to do with the help of the virtual memory system. So, you have a huge amount of memory which is available as your secondary storage, but a limited amount of memory as your physical memory, as your main memory. So, how do we manage these two, and that is how do we manage a smaller size physical memory yet give the appearance as if you are working with a very large memory. That is what virtual memory tries to do for us. So, to explain that a little further, if we look at the addressable memory space that we have, the addressable memory space depends on the number of address bits in a computer. Okay. So, if your address bits, for instance, we have already looked at the control unit and so on, right. So, we have seen that as the output of the control unit, you will have a certain number of address bits which come out, which will go and address the memory. If your computer supports, let us say 32-bit addresses, then the addressable memory space would be 2 to the power of 32, okay, assuming that they are all byte addressable locations. So, you will have a total of about 4 gigabytes. So, 32 bits you can go up to 4 gigabytes. Similarly, if I have 64-bit addresses, you can go up to 2 power 64. So, that comes to about 16 exabytes. But the physical main memory that we have is obviously not as large as this addressable space. So, we are talking about 4 gigabytes and we are talking about multiples of exabytes and so on. So, your physical memory is definitely not at that larger space. Normally, physical memory is limited to just about a few gigabytes, a few hundred megabytes to a few gigabytes. That will be the range of physical memory that we normally have on most of our systems. Of course, very powerful scientific processing systems may have a larger physical memory, but if you take most standard computer systems, this is where the physical memory range will be, a few hundred megabytes to a few gigabytes. So, the question is, if I have a very large program which does not fit into my main memory, how do I handle it? So, what we are saying therefore is, if a large program cannot fit completely into the main memory, we will have parts of it stored on a secondary storage device such as a magnetic disk, right, and transfer pieces of programs to the main memory from the secondary storage before they can be executed. So, just when I need to execute them, I will transfer them from the secondary storage to the primary storage, to the primary memory, and execute it from there. So, what we are looking at is, store your large programs on your hard disk, but bring in only that portion of it which is required for execution to the main memory and execute it. So, this is what we are trying to do with the virtual memory system. So, what do we need therefore? We need some techniques which will automatically move the program and the data between main memory and secondary storage when they are required for execution, okay, and these are what are called as virtual memory techniques. Okay. So, we call it as virtual memory because this is different from the physical memory that you have. The physical memory is limited in space, but you are able to execute a program which is much larger than it. So, giving it an appearance as if virtually there is a lot of memory. So, it is a virtual appearance. So, we call it as a virtual memory technique. When we look at programs and processors, all of them reference an instruction or data independent of the size of the main memory. So, the programs and processors, they will reference instruction or data depending on the size of the address bus that is available. So, we said that if you have a 32-bit address, we can go up to 4 gigabytes, right. So, if I have 32-bit addresses and I can go up to 4 gigabytes, my programs can be up to 4 gigabytes large. So, that is the kind of memory that the programs and processors will address. Okay. Your main memory may be much less than that, it does not depend on that, your programs still should be able to work. That is what we want to achieve with the help of virtual memory. What we say is, the binary addresses which are issued by the processor, okay, they are called as logical or virtual addresses, okay, and these virtual addresses are, they go up to 2 to the power of, if you take a 32-bit address bus, your virtual address can be up to 2 power 32. But if you have only a, say, a 512 MB physical memory, your physical address will be only up to 512 megabytes. Okay, so that is the difference that we have: physical memory address, and logical or virtual addresses which are generated by the processor. So, binary addresses issued by the processor are called logical or virtual addresses. This is what we need to remember. So, the next question that comes is, now I need to be able to translate from this virtual address to the physical address. Okay. So, this translation of virtual address to physical address, okay, that is normally done by a combination of hardware and software subsystems. The software subsystem that we use is normally the operating system. So, operating system plus hardware, both these together help us to achieve this virtual address to physical address translation. So, now virtual address is the address that is produced by the processor, which can go up to the full capacity of the processor's addressing capability. Physical address will be the address which is generated to access the physical memory, which will be limited in capability. So, I have a large virtual address which is to be mapped to a smaller physical address. That is what I need to do. So, what do I normally do for that? What is the requirement there? The requirement is that if the virtual address refers to a part of the program that is currently in the main memory, it is accessed immediately. Okay. But if the address refers to a part of the program that is not currently in the main memory, then it is first transferred to the main memory before it can be used. So, we are looking at virtual addresses, assuming that virtual address is referring to a physical address which is already there in main memory. I am assuming that I have already brought the data into main memory. So, if it is already in main memory, I access it immediately. If it is not in the main memory, obviously I will have to transfer it from the secondary storage to main memory before it can be used. Obviously, the first time that I access a program, it will be only in the secondary storage. From the secondary storage, therefore, it has to be moved to the main memory, and then you can start executing it. Okay, that is what will happen. Okay. So, once I brought it to main memory, if I am continuing to use memory locations which are there from the portion that I have already brought to main memory, then you keep accessing it from the main memory. But the moment you address something which is not there in the main memory, you have to go and transfer it from the disks, from the secondary disk space that you have. That is one aspect. Second thing we also need to look at when you are looking at such a virtual memory system is that if a new piece of program is to be transferred to the main memory and the main memory is already full, okay, what do we need to do in that case? So, we said that initially of course we can assume that the main memory is completely empty, so you keep transferring things into the main memory and work on it. So, let us say you have been working for some time, you already have different programs running from main memory, and let us say the main memory is full. Now, if a new piece of program is to be transferred, what do we do? So, a new piece of program is to be transferred, and if the main memory is full, what we need to do is you need to replace some portion of the main memory. Okay. So, some other piece which is there in the main memory must be replaced, and you have to bring in your new piece. Now, remember, this is very similar to what we actually do in the case of cache memories as well. We have seen that in the case of cache, that you have limited amount of cache size, main memory size is larger. So, when we bring things from main memory to cache, we will replace things which are already existing if there is not enough space in the cache. So, the same idea has to be used over here. So, we will need some replacement techniques just as in the case of cache. Okay. And normally this replacement plus this managing of memory is handled by the operating system plus the hardware, and the application programmer is normally not aware of the size of memory and this transfer that is taking place. That is how the system is designed. So, you design the system such that the application programmer should not be aware of this entire operation that is taking place. So, this happens behind the scenes, so to say. Okay. So, the operating system plus the hardware will automatically take care of doing all this data transfer, doing all the replacement and whatever is necessary. Okay. So, that is what we have in terms of what virtual memory does. So, another way of looking at the same thing will be, since we have already looked at cache, if we look at a comparison with respect to what happens on cache. So, just as we said that from main memory we transfer things to the cache, you can look at main memory as a cache for the secondary disk storage. Okay. What is a cache? It is supposed to be a place from which things can be accessed faster, right. So, from main memory we brought it to cache. Now, all we are saying is from disk we will bring it to main memory. So, main memory you can say acts like a cache for the disk storage. So, once we do that, then the CPU plus OS, as we said, translate the virtual addresses to physical addresses and manage this entire system, and the structure used for doing all this translation is normally referred to as the memory management unit. So, this is important. So, we need to understand how this memory management unit is organized. So, we use certain structures for doing all this translation, and all that goes under the name of MMU or memory management unit. Okay. And when we look at different programs, we also have to understand that different programs may be sharing main memory. So, in which case each program will get a private virtual address space to hold its used code and its data. Okay. And normally one program's virtual address space will also be protected from other programs. This is important because you can't have interference between programs or one program corrupting another program and so on. Okay. So, the virtual address space has to be kept separate, and normally all these things are handled by the help of OS and virtual and the hardware, and all this comes under the purview of a memory management unit. So, you look at how these things are done. So, if we look at where this memory management unit will actually be located, okay, you will see that it is normally located between your processor and the access to the cache. Now, we said the cache is normally accessed by means of physical addresses. So, you have a memory management unit which takes the virtual address which is produced by the processor and converts it to the physical address. So, once you convert it to the physical address, then you can take it from the cache, and if it is not there in the cache, we get it from main memory and so on. Okay. So, this is the overall process. The MMU as such, okay, this is where it is located. Now, we need to look at how this MMU will actually do all the translation. So, we will take a short break and come back and look at the details of this. Welcome back after the break. So, we are just looking at what virtual addressing is and what is done in a virtual memory organization. So, as I said, we use something called a memory management unit which is responsible for translating virtual addresses to physical addresses. Remember, virtual address is the address that is produced by the processor, which can address a space which is much larger than the physical main memory. So, a larger virtual address is mapped to a physical address which is smaller in size by the memory management unit. So, let us look at how this translation actually is done. So, if we look at this address translation, you can look at it as a table, right, which translates from virtual addresses to physical addresses. Okay. So, how is this translation done? How is this table organized? That is what we need to understand. Okay. So to do this, what we do is we divide memory into blocks, right, just as we had divided cache and main memory into blocks and then the transfer in terms of blocks. Similarly, for data transfer between the main memory and your secondary storage, we divide it into blocks and always transfer data in terms of blocks. Only thing, the blocks are typically referred to as pages. Sometimes we use something called segments, but a more common methodology is to use a paged virtual management system. So we refer to these blocks as pages. So you can look at a page as consisting of a set of words that occupy contiguous locations in the main memory. And size of a page commonly ranges from 2 kilobytes to 64 kilobytes. Now there is always a trade-off that we have between size and performance, right? So if you look at small pages are not good in the sense that if you had a small page, you will go to secondary memory to access that page, but because the access time of secondary storage is much larger than the main memory, okay, it is not an optimum access time in terms of accessing these small pages. That is, I am having a small page, so I will go to main memory, I will wait for the main memory to access that and then transfer that, to first of all go and access that particular page and then transfer it. There are two components to it. That access time normally happens to be much larger than the transfer components itself. So if I access it, but I am going to transfer only small portions, then the overhead of access becomes larger. Okay. So in that sense, small pages are not good, they don't give us good performance. But if we use large pages, which is obviously the other option, right? So if we use large pages, what can happen is that you will bring a large page into memory, but that page may not be entirely used, in the sense that there may be only some small portion of that page which actually contains valid data. So there may be a large page that has come in, but it is actually not being used fully. So in that case also it can lead to some underutilization. So this is a problem that we normally have. So whether we go for small pages or large pages, so you have to always strike a balance between the two. Okay. So it has been found that ranges between 2K to 64 kilobytes work generally well. Okay. So this is what we will find in most of the processors today. So if you look at how this translation actually gets done, the virtual or logical address is interpreted as a virtual page number plus an offset. That is, you have your whatever 64 bits or whatever number of bits we have, right? So that is treated as virtual page number plus an offset. That is, the entire address which can be looked at as higher order bits representing a virtual page number and the lower order bits representing the offset. Okay. What do I mean by this offset? It is just it specifies the location of a particular byte within that page. So the virtual page number will tell you which page number you are referring to, and this offset will tell you which byte within that page you are referring to. Both these put together uniquely identify the byte that you want to refer to. And the page table will store information about the main memory location for each page. So areas of the main memory that can hold a page is called as a page frame. So you kind of move it from a page to a page frame. Okay. And the starting address of the page table is kept in a page table base register. Okay. So these are the different terms that we use, and these are the different concepts we use in order to do the translation. So we can understand this with the help of a diagram here. So I have a virtual address which is divided, as I said, into two parts, right? A virtual page number and a page offset. So the way this will get translated is like this. So this virtual page number will be translated to a physical page number. Okay, and once this translation happens, I will take this physical page number and add this page offset to it and get my physical address. So this is what needs to be done, from virtual page number to map to physical page number. To do this translation, we need to do some extra work. Okay, so you can see what is typically happening here. So virtual addresses which are larger in size, right? So they will be mapped to physical addresses. Okay, and that is what is happening through this memory system, that this MMU that we are talking about over here. So between this virtual address to physical address, this address translation has to take place. So we have this virtual address which is coming from the processor, as I said, which consists of virtual page number and an offset. Virtual page number is used to convert it to the physical page. This is what we do. So you take this virtual page number and take this page table address which is available in the page table base register. Okay. So this page table base register, what this actually does is it is pointing to the beginning of the page table. So you have a page table where you have the physical addresses which are stored here. Okay. So if you look at this page table address comes from the page table base register. To that value you add this virtual page number. So when we add these two, this provides the entry of the page in the page table. So we take this page table address, right, which gives me the base of the page table. To that I add this virtual page number. When this added value, this result tells me the entry of the particular page in the page table. So corresponding to that entry, I have whatever information I want. I have the starting address of the actual page, the physical address. So that physical page number comes from this entry for me. Okay, and to that, if I add this offset which I already have here, that gives me the total physical address that I need to access main memory. Okay, so this page table, if you look at, each entry will have a certain number of control bits plus the actual address which is required to access the page in memory. Okay, so these are the various components that we have. Actually, if you look at this, this is a very simple translation which is done. All we have is, we'll just look into the page table and then look at the corresponding entry and get the corresponding physical address. Only thing, we have a page table base register to point to where exactly the page table is located. This page table itself will have to be located somewhere in memory. So if this page table is located in memory, I need to know where in memory this is located. So to specify that, we have this page table address. Okay, so that is why we use a special register called the page table base register, using which you identify where the page table is located, and from that, if you add this page number, you get the corresponding physical page number and you can get the physical address for the main memory. This is all that we have. It's a simple process. So this is all that we need to do for doing this. So now if you look at this page table, look at all the entries that are there in the page table. If, for instance, let's take a look at that. This page table, as we said, is an array of page table entries. It is indexed by the virtual page number. So if the page is present in memory, okay, how do I identify that the page is present in memory? If it is there in memory, if I have a valid bit set for this particular page, I said we have control bits that are present over here. So the control bit indicates that it is a valid bit, okay, then which indicates the page is present in memory, then we say we have a page hit. If we have a hit, then we can directly access it from the main memory. In addition to this valid bit, there are also other status bits which are also stored along with these control bits that we have here. Okay, we have bits called the referenced bit, we have a dirty bit, and so on. We'll come back to what the purpose of each of these bits are a little later. Okay, but with the help of these status bits, we are able to handle the memory locations quite effectively. Okay, so we have these additional status bits. So once I have a hit, then I can access it directly. If the page is not present, then we say that we have a page miss, or what is also called as a page fault. Okay, if I have a page fault, then I need to refer to a location in swap space on the disk, and I need to go and get it from the hard disk. Okay, that is what we need to do. The page table entry now needs to tell me where in the hard disk it is located, and I need to get it from the hard disk. The fields that we have in each page table entry, the fields are this. You will have the physical page number, you will have the control bits. Out of the control bits, valid bit will indicate the validity of the page, whether it is present or not, and then there will be a modified bit or a dirty bit, which is very similar to the modified bit or a dirty bit that we also used in the cache. This bit will tell me whether this particular page has been modified or not. Remember, if it has been modified, then it should be written back when I replace this page. If it has not been modified, I don't need to write it back. So for that purpose, we need to have this modified or dirty bit which is specified. Okay. So with these two control bits, you can almost get the basic operation of the virtual memory subsystem. There are also other control bits are used for permissions on page access. For example, certain pages you may have only read access. For some pages you may want to provide a read and a write access. Now this often happens when you are looking at certain portions of main memory which have to be accessed, for instance, only by the operating system or only by certain programs which have certain privileged access and so on. So all these permissions can also be set along with this page table entry. So these control bits are used for all these purposes. So if you look at this translation, let's take a look at this with the help of our valid bits and see how this whole thing is done. So as we just said just now, the page table register will point to the beginning of the page table. The page table is located somewhere in memory, so this is pointing to this. And from the virtual address, I get the virtual page number, right? So this virtual page number will tell me from the starting position where exactly this is located. And you can see that there is a valid bit that will be there along with the page number. So if this valid bit is 0, it indicates that it is not present in main memory. If it is 1, then it is a hit. Okay, so then this address is pointing to the physical page number. So then I can construct my physical address. I construct my physical address by concatenating the physical page number with the page offset. Okay, so you can see this is an example where we have gone from a 32-bit virtual address to a 30-bit physical address. So 32-bit virtual address, 12 bits, and I am assuming that I have 2 to the power of 12, right, so which is about 4K of page size. So with a 4K page size, I need 12 bits to access each page, the different bytes which are there within each page. So 12 bits are used for the offset, and the rest of the bits are used as the virtual page number. So this virtual page number 20 bits is translated to a 18-bit physical page number, to which this 12-bit offset is added to get back my 30-bit physical address. Okay, so this is how the virtual address to physical address mapping would actually be done. So now we can look at what is happening if the valid bit is 0. Now I said that if the valid bit is 1, the entry here will point to the physical memory here. So you can see this, wherever there is a 1, you have the physical page table pointing to the corresponding table in physical memory. If it is 0, this will point to where I need to get it, it will point to the disk storage. So I need to get the data from the disk storage and then bring it to a corresponding location here. You may have to replace some existing data that is already there, okay, those are things we will look at later. But if it is 0, typically you need to get it from disk storage and then bring the data into this corresponding position. So that is what we are showing by means of this picture, where we are showing both 1 and 0 here. So once we have looked at the translation and we said that everything is done with the help of this page table. So the next question that immediately comes up with, where exactly is this page table located? The page table has to be used by the MMU for every read and write access to the memory. Okay. So which means this access has to be really fast. Okay. So ideal location for the page table will be within the memory management unit, okay, but often the page table is quite large. So it is not possible to include a complete page table within the MMU, which is within the chip itself. So normally what we do therefore is, we keep the page table in main memory, but a small portion of the page table is accommodated within the MMU. So using that small portion, which can again be treated like a cache for the page table, we are able to effectively get a faster access for the page table and do this address translation that we are talking about. Okay. So this is basically how the virtual memory subsystem essentially works. So to summarize, what we have looked at in today's lecture are the following. We basically looked at virtual memory, what, why and how, what exactly it is, why we need it, and how virtual memory is established or how it is implemented. Virtual, we also looked at in the details how the address is translated, that is how is virtual address mapped to the physical address, what we call as address translation. Then we also looked at something called a memory management unit, which is responsible for doing this translation, and we saw that memory management unit does it with the help of page tables, and we also looked at the details of the page table entries and how the translation actually gets done. A set of questions to review the concepts that we have covered today. Question number 1, why do we need the concept of virtual memory? Question number 2, what is a virtual address and what is a physical address? Question number 3, what are pages? Question number 4, how is the translation of virtual address to physical address achieved? Question number 5, what are the entries in a page table? Thank you.